Halloween's not a recognized holiday, so it's every witch's demise. So. All right, so I have some notes first. This is just some facts that you need to know. So we're going to talk about the absolute. We're going to talk about absolute maxima and minima. So absolute maxima and minima. Hi there. So when we start talking about this, they always start with some sort of notation where we have some f of c value is a local maxima if f of x is less than or equal to f of c for x near c. For x near a c. And the local minima, we would say f of x is greater than or equal to f of c for x near c. And so we're interested in the largest or smallest values. So these are the largest and smallest values of f of x throughout the domain. So let's add that, throughout the domain of f. So it's a lot of fancy talk. For the following diagram. And you'll see the connection. So one of the diagrams that I'm going to talk about, I'll tell you what, I'll do the first one that they give us. So as soon as you're ready, here we go. So let's say hypothetically, they're giving us the formula where f of x is equal to x cubed over 3 minus 4x. Okay, so what I'm going to do is I'm just going to throw it on the screen for you. So go ahead and write down the function if you'd like. And let me go out to Excel. And I'm just going to use plain old Desmos, which I already told you guys, feel free to use it, and I would recommend that you do. So where we have f of x is equal to x raised to the third, and all of that, go over 1, all of that is divided by 3, and scooch over a bit. And here's your 4x, and it looks a lot like that. So you took the notes down, you're taking the picture down. Here's a coordinate point, crossover, here's another coordinate point, there's another coordinate point. So when we talk about the maxima, I'm looking at here. When I look at the minima, I'm looking right here. Now, we could do the math. So as you see it visually, it's pretty blunt or blunt. This looks like if you plug in the negative 2 for as an example, you end up with 16 over 3. 16 divided by 3, which is 5 1/3, which is 5.3 repeating. And so that's our local maxima. Our local minima is going to be basically the same thing, except it's positive 2, negative 5.3 repeating, which is also 16 over 3. In essence, all you're doing once you solve for this, in this case, we have negative 2 cubed over 3 minus 4 times negative 2. So that's analyzing the value. So you do have a local, like I said, this was the negative 2, f of negative 2. This was a local maximum. Call this a local maximum. And when we look at the other side of the function, we find 2 cubed, or 2 cubed minus 4 times 2 with this over 3. And this also ends up in the same point. So the local minima is this one. That's what all this fancy notation up here is referring to. Basically, if I plug in any x, as I approach that x, what's happening to the diagram? Is it increasing left to right, or is it decreasing left to right? And that point is either the highest of all the points or the lowest of all the points. In essence, that's what they're telling you in the diagram. I'm thinking if I differentiate this, what would happen? Let's differentiate this. Wouldn't this be 3x to the second power? It's times 1/3. So it's 1/3 times this minus 4x, which is just going to give us a minus 4. Would you argue that the 2 points that we're looking for would be x minus 2, x plus 2? Because technically these are canceled out, leaving you x squared minus 4, which if you factor them, that's where you're getting the plus 2 minus 2 that we're substituting in here. And that's telling us where our values are. So one more element that the example that I could use for you here is, let's look at the parabola. So they do give us, I'm trying to give you guys that came in late a little bit of time to catch that writing. Are you good? Or do you need a minute? You good? Yeah? Okay, the next example they do give us is if I have f of x is equal to 4 minus x to the second power. And so let's graph it. Let's also graph this one. So I'm going to take this down. So I have 4 minus x squared. What do you notice? Yeah, it looks to me like there's one turn. You know the concept of turns, right? Like if it's cubic, how many turns do you expect?
3.
2. 2. If it's cubic, you get 2. If it's quadratic like this, how many do you get? 1. It's always the highest power minus 1, always. So if I have y equals x cubed, how many turns? 2. If I have y equals x to the 4th, how many turns?
3.
I would expect 3 turns, yeah. Do you want to see an x to the 4th just for the sake of the, whoa, and that's 24th, so. This actually seems to only have one turn. It's probably missing something else. But typically x to the fourth power do tend to, let me see if I can do this. No, it's not showing.
Wait, zoom in.
Yeah, it's a lot of zooming. But yes, it will have 3 turns. It actually looks like a W. For example, if I have x squared or x cubed, for example, 1, 2 turns, where I have max and min of some sort. If it's x squared, I should only have 1 turn regardless of the direction. When it's x to the fourth power, yes, it's 3 turns, and it looks like a W because it does this behavior. Okay. Quintic, same thing. You know, they eventually start to fold in, but yes. All right. So in this case, I have 4 minus x squared. If I took this derivative, what would I have? Well, minus 2x. So right now, let me go back to my square. And then what did I say? I said 4 minus x squared. So 4 minus, minus x squared. There you are. You see that 4 is 0? That's the absolute maxima. And in this case, we do not have a minima. Okay? Another example that they give us. So we said for this one, 0, 4. And we said in this case, this is an absolute maximum. Absolute max. Okay, and the third diagram we have is f of x is equal to x raised to the 2/3 power. So this is a tricky one because this one actually does this fold out of the origin. So if I go back, that's what it does. So in this case, you would say 0, the origin basically is the absolute minima. There is no maxima because it just fans out. So yeah. So having shown you these 3 diagrams, let's discuss another piece here that they mention in the text. And in the text, they state the definition. So the actual definition of an absolute maxima or minima in this case it says if, it's going to sound very redundant to what we just discussed, if f of c is greater than or equal to f of x for all x in the domain of f, then fc is called the absolute maxima of f, of the function. And I showed you an example, a couple of examples. If f of c is less than or equal to f of x, then for all x in the domain of f, then f of c is called the absolute minima. And we're going to explore some graphs, and you'll see the difference as we explore and see which actual points are considered a minima versus a maxima. You also will hear this referred to, so we're going to say that an absolute maximum or minimum is called an extreme, an absolute, oh my god, absolute extremum. All right. Let's look at some figures. Let's go with that. And so one of the examples that they give us is they're looking at a particular function. So they're saying if we're looking at absolute extremums, so if they give us f of x is equal to x cubed minus 21x squared plus 135x minus 170, we're going to look at it at various intervals. So what they're saying is we could take this diagram, and so let's go ahead and let's draw the diagram. I'm going to go ahead and show you the diagram first on Desmos. So we'll go with Desmos first. So x cubed minus 21x squared plus 135x minus 170. As you can see, it is a very large diagram, right? So as I pinch it as much as I can, there it is. That little thing is what we're looking at right there. So I'm just focused on that little zigzag right there. So what they're saying here is, for example, if I analyze this little zigzag at various points, so get that framework in your mind in terms of what I'm looking at, which is just right there, just that area. And if I bring it down here, you notice I'm looking at values. It looks like anything from 2 to 12, 2 to 11. So that's about where I'm looking at. So if you want to mark it off, so for example, x equals 12, right? So that's one of my kind of like vertical cutoffs in a sense. I guess I could go, let me see. Could I look at 0, maybe 2? Let's go with x is 2. So my x is equal to 2. Not 12, 2, dingbat. All right, there you go. Do you notice that I'm kind of like framing it so that I only capture that zigzag? Mm-hmm. Right? So that's the idea. I'm sort of compressing it. It's all, if you've ever looked at the TI 8384 calculator, I could potentially use that here too. I am recording, don't panic. Let me see if I can pull that calculator up real quick. Yeah. Okay, so I can capture the window. They're asking us to do so. So I don't know if you're going to be able to see it up here, but I need you to give it a moment and see if you can capture it as I plot it for you. So x raised to, forgot it's picky. x raised to the third power. Okay, minus 21 x raised to the second power plus 135x, damn it, so picky, minus 170. Okay, so I'm going to go to graph, and it's going to go nuts because that's all I can see, right? That doesn't help much. But if you go to the window, I can change my max and min since they want a 212, so this will be 2 and 12. And that should be enough for me to go back to the graph. See how it's starting to narrow me down here. I'm gonna go to zoom. Let's go to zoom out. If it takes too long, I'm not gonna do it, but it's taking forever because it's going all over the place. So we're looking at the values of x between 2 and 12. This is taking too long, I'm sorry. If I can do it at home, I will. But that's all they're doing, is they're looking at here, from here to here. So with that said, now that you understand that I am using an actual drawing, this drawing, when I look at the interval, so I'm looking at from 2, let's assume x is 2 here, and here's 12. This diagram is doing this behavior. So it's doing this and this, because that's what I'm looking for, or looking at. So if I'm starting at an f of 2 and I'm saying that this is inclusive as a window, that's one value. So my absolute minimum, believe it or not, in this case, and that is because the 2 and the 12 are inclusive. So I'm specifically saying the window is when x is 2 through when x is 12, and that is inclusive. So I'm actually throwing that value in here. I'm getting, so this is f of 2 plugged into formula will give me 24. So in other words, 2 cubed minus 21 times 2 squared plus 135 times 2 minus 170, that all totals 24 basically. Okay? All right. That's the minimum. Absolute maxima. So I'm going to put ABS max, absolute maxima in this case, is when you're looking at f of 12 is equal to 154. Now, I need you to pay attention because it's in the devil is in the details in this section. And so when I'm telling you that the fact is that these are inclusive is what makes those endpoints important. Okay? When I show you the next example, it's not going to be as important because now I'm looking at the value 410. So if this is 2, let's say this is let's say this is 3 and this is 4. Let's say 4 is here. In this case, I actually reach my absolute maxima at 5. So here's 4, 5. So let's pretend this is connected. That's my absolute maxima here. So it changes, right? The whole script just changed on you. And as I pull closer, f of 9, for example, if this is 9 here, f of 9 is going to give me 73 for a value. F of 5 I said was 105. Did I not say that? No, I didn't. So f of 5 is giving me a value of 105. Whereas f of 9 is giving me a value of 73. And this makes it the absolute minima. So ABS, absolute minima. Okay. even if I were to look at this interval specifically from 4 to 10, so let's say hypothetically I'm at 10 here, I'm going to make that 10 in red. You already start to see that it's reaching the 9 and that it should be dropping. And the idea is, as you see it drop, you're trying to reach that number where it's the lowest of the low and this is the highest of the high. What I find interesting is that in the textbook they're showing you this and they're still talking about these values in terms of absolute minima and maxima, yet they're slightly different. In the next example, the third example, same diagram, the same capture, but this time they're looking at the window. I'm doing it in purple, where x is 4 and y, and its other extreme is 8. So again, from 4 to 8, remember this is 4 here, 8 would be just inside of here. If that's the case, then they're arguing that this is still the maxima, this is still the minima. And then they're squeezing it further. They're opening up to 3 to 11. Let's do that one in blue. From 3 to 11. These are the values of x. So if this is 3 over here, and I'm looking at it from 3 going up to here, they're saying that this is still the max. And f of 11 in this case is matching this height, and this becomes the new absolute. In this case, it's also an absolute maxima. So that's also an absolute max in the event they were looking at the values 3 to 11. So in essence, they're looking at the window. They're looking at windows, different intervals. If it wasn't for the interval, that's what's really dictating what's happening here. Is it clear or not? Pretty easy? All right. All right, so let me talk you through the couple of definitions. So we'll start with this definition. This is locating an absolute extrema. Sorry, the pen is, I'm having problems with the, so here's your absolute extrema. So absolute extrema if they exist, must occur at critical numbers or endpoints. Must occur at critical numbers or at endpoints. Okay, so I'm going to walk you through example 1. And example 1 has several steps, so just bear with me as we go through the steps. And by the way, I think there's only 3 examples in this section. Am I wrong? 3 examples, okay? So be patient. It's just tedious. That's why some of you are dozing off. I'm observing you. So absolute. So we're finding, and these are the steps you're going to follow. Finding the absolute extrema. Okay, so they want us to find the absolute extrema and minimum given the function. They're giving us f of x is equal to x cubed plus 3x squared minus 9x minus 7 on each of the following intervals. So on each interval, this is where you're going to either get this or you're not. So pay attention. I'm going to start with the first interval. So in part A, they're asking us to find it between the interval where x is -6 and +4. So let's take this. Can we find the first derivative? So if I take the first derivative, I'm going to get 3x squared plus 6x minus 9. I'm going to factor out the 3 because 3 goes into all 3 of these, right?
Mm-hmm.
So if I factor out the 3, I'm left with x squared plus x.
2x.
2x, x squared plus 2x minus 3, which I can now factor further, and I get 3 parentheses x minus 1 times x plus 3. All right. So my critical numbers, basically, so pay attention to this. I'm going to write them in red. The critical numbers for this particular function are x is equal to +1 and -3. Now we want to evaluate the endpoints. So we go back to that number line concept, and we start with, if I'm looking at the endpoints, I'm looking at f of -6, right? Because remember our endpoint was -6 and 4. So we're going to start with f of -6 and f of 1, f -3, which should have been before that one, and f of 4. So you can use whatever method to get this answer. Do you know how to do that without suffering? How many of you have the TI-8384? Is this as easy as plugging it in, right?
Yeah.
So let's use the function. Let's go to y equals, and we're putting in the x cubed. If not, you're going to suffer and have to do this step by step. So x, oh my god, x raised to the third plus 3x raised to the second. Oh my god, I promise you I'll get myself in order here. X raised to the third. I'm not having a good day today. Let's leave it at that. Plus 3x raised to the second. Do it again. It's just, it's very picky. Okay. We're good there. Minus 9x. Did it again? I did it again. Minus 9x minus 7. Okay, so now that you have this in here, you should be able to go to second graph.
Oh.
I know what it is. It doesn't like negatives. It wants the integer sign.
I think it's because of that arrow before the x cubed.
I could get rid of that too. Delete that. Oh, I have to click on it. Yeah, it doesn't like these to be negatives. So you see that subtraction sign? Yeah. It's like, no thank you, let's use an integer. Same thing here. I have to change it to the integer. So anyway, if I go to second graph, there's my table. This is really good. So I need -6. There's something wrong with here because this should be -61. Let's see what went wrong. Nah, it's too big. Okay, so it should be x cubed plus 3x squared minus 9x minus 7. Let's do it mathematically then. Fine. It should be working just as I stated.
Would
but
it be the fact that you haven't changed the way back to its normal form, or no?
the what?
Forget I asked.
What? Alright, so this is equivalent to, we're all gonna suffer this one. Negative 6 to the third power, plus I'm sorry, I just noticed why this is off. We're not gonna have to suffer at all. Use a derivative function. That should give it to you. Dumb mistake. All right, so we're using the derivative. So 3x raised to the second. Doing it again. Okay, 3x raised to the second. Okay. I promise I'm not messing up this time. Plus 6x. So let's see, plus 6. Use the calculator. Plus 6x. Okay. Minus 9. Okay. If I go to second graph, it should. There you go. Is it still wrong? This is negative 6. Negative 3 should not be 0. It should be 20. ¿Por qué? And this should be negative 12. No, this is wrong. I'm telling you, let's just do it by hand then. Alright, did anybody do this by hand? What is f of negative 6? What did you get?
Negative 61.
Look at that. In one shot. Negative 61. Did you do f of 1?
Negative 12.
Negative 12.
Mm-hmm. Okay, did you do f of negative 3?
20.
Positive 20, right?
Mm-hmm.
And the last one?
69.
69. So the question then becomes, which is the largest number out of this group? 69. So f of 4 is the absolute maximum. And I drew them out of order, thinking I was going to be slick and trick you, but I managed to screw myself over, so. So this is our max. Our max is going to sit somewhere here. Which is our min? What's our minimum?
6.
Yeah, negative 61. So it looks like we can tell that this is our absolute minimum. So our min is here. We know whatever's happening, it's going to be something like this. All right, we're going to repeat the same process for the same, but now we're going to look at another interval, same equation. This is the interval negative 4, 2. See what you get for that one. We're still going to use, in this case, so here's your x values to use. This is f of x. And we're going to start with negative 4, negative 3, 1, and 2. So where's your minimum? Which is your maximum? I'm getting, we already had this one, right? This is 13. Negative 3. I'm getting 20. Negative 1. Minus 12. And 2. Minus 5. So which is our maximum? This is our maximum here. And our minimum? Absolute minimum, maximum, by the way. All right. And part C. They're asking us to look, and again, remember, you're using the same function. We're just looking at a little, almost like when you take your binoculars and you focus on a specific area, right? Does that make sense to you when I say that? So we're looking at the same diagram, but now we're focusing on this -2 to 2. What's happening? If I do a t-table, what am I getting? -2,
15.
+2, and 1. Yeah, so 15, what'd you get for 1? It was -12, right?
Yeah.
And for 2, we got -5 in the last time. So we have an absolute, and just this interval, absolute max and an absolute min at -12. What do you think about this one? Does it marinate to you?
Yeah.
How we're gonna,
Yeah.
it's pretty easy, right? Let's see what's wrong with my calculator and what it's doing what it's supposed to be doing. All right. So that's example 1. Let me run to example 2. At least take a little bit of time. So in example 2, there's a little bit of information about the second derivative and its rule. Okay, and we're going to use this as a test for local extrema. So they're basically saying let C be a critical number. So let C be a critical number of f of x such that the first derivative of C is equal to 0 if, and this is the rule that I really want you to pay attention to, if the second derivative of C is in this case greater than 0, my bad, it's greater than 0, then f of C is the local minimum if that second derivative of C is less than 0, then f of C is a local max. Maximum. These definitions seem very simple, and they are. So let's look at what, as a chart, what they mean. So if I have the first derivative of C compared to the second derivative of C, and we talk about concavity, so let's look at the graph of the original function. If we look at f of C as a point, and I'll give you an example here. So the first derivative, you obtain a 0 value for all of these. And in the second derivative, there's a positive, a negative, and a 0. You understand that this is concave up, this one is concave down, and this one is unable, you'd be unable to detect. So a local min for f of C, where you have basically something like a parabola going this way, a local max where you have perhaps a parabola going this way, and in this case the test does not apply. So let's do an example of each, and this is basically example 2. Okay, and example 2, I'll leave the graph there so you can see it. They're giving us, we're starting with f of x is equal to 4x cubed, plus 9x squared minus 12x plus 3. This is A. Gonna leave a little space and we'll put in the answer. B is simple. B is f of x is equal to x times e raised to the negative 0.2x. All right. And in part C, we have f of x is equal to 1 over 6 x to the 6 minus 4x to the 5th plus 25 x to the 4th. So those are the 3 questions we're going to look at. And so I'm going to start with the first question, and I'm going to do the first derivative here. So f first derivative is going to give me 12x squared plus 18x minus 12, which I can further factor if I take out a 6. That's going to give me 2x minus 1 and x plus 2. I'm just factoring after dividing. It looks based on this information here, which now after having written all that, I'm going to actually delete it because I need the space. I may end up just doing one of these or maybe 2. I don't know. We'll see. Okay, so that means that my critical numbers, look up here, critical numbers are quite obvious, right? They're right here, this one and this one. So x is equal to negative 2 is one of my numbers, right? And x is equal to positive 1/2. So now let's take the second derivative of this equation. So f, second derivative of this is going to give me 24x minus 18, I'm sorry, plus 18, which if I factor this, 6 goes into both of those, so this will be 6 parentheses 4x plus 3. And what I want to do now is substitute in that negative 2 and again the positive 1/2. And so in this case, notice that this results in negative 30 and this results in positive 30. Where you look at this is a negative number, this is obviously a positive number. So we know in this case, based on the definition, this is a maximum. There's a maximum at negative 2, and I know that this minimum exists at positive 1/2. Okay, let that marinate for a minute. Let me take you to Desmos for a second. I like using Desmos, it always works. Okay, and what do we have here? We have 4x to the third. Let's take a look at 4x to the third. I want you to see the big picture, see how this relates. Positive 9x squared minus 12x and then plus 3. Where's the diagram?
because it got equals instead of minus.
My life sucks. I swear, when I do stuff like that, I get so upset. You guys don't know that when I make a mistake, it's like the universe has just stopped. Everybody in the universe is looking at me going like this. It's like up here. Okay, so here you are. What do you think? Let's look at x is equal to -2. Do you agree? And let's look at x is, what was the other one? 1/2. So x equals 1/2. Make sense? Yeah.
How do you get Desmos to give you the order pair?
It just doesn't. Just when you click on the, actually, as a matter of fact, in this case, it happens to do it right away because there's a distinct point. If you want another point, let's say hypothetically, I don't even know where my picture
You
is.
just click anywhere on the line.
Yeah, if I click anywhere, like here, see? It's gonna give me a point, so I could keep, as long as I'm on a point, I could move the point up and down, and so.
What are you clicking to get the black one?
Just the figure itself. So if I unclick it, now these little points are gonna pop up because they're significant anyway. Yeah, so that's the beauty of Desmos. You can make them go away. That's what I'm trying to do right now. Yeah, but you can play with it. So you can see the little gray point here. That was my Maxima, right? On this one. My Maxima, which is at 31. And it's gonna show. It'll show. Okay. Is that one clear? Easy, right? I don't need to do the other two, do I? So I'm running out of time. I want to make sure I do example 3. Do you want one more or not? Yeah, okay. All right, I just want everybody to be happy. This is why I'll never be president of this country. Okay. Not that I ever thought about running, so. All right, example 3. So we're going to talk about the absolute extrema, but I am going to give you some notes here. This is like their theorem 3. So this is the second derivative. May I mention something just on observation? Like in chapters 2, we went through the whole thing. Chapter 3, we went through the whole thing. This chapter, they missed a couple of sections. They don't want us to cover it. I personally would recommend, even if you just read it for a couple of seconds, just take a look and get the vibe of what they're getting at. It'll help you quite a bit on understanding the big picture of this subject you're looking in. So this is a second derivative test again. And same thing for absolute. I'll try that calculator thing again and see why it didn't work. Absolute extrema on an interval. All right, and so what it says in this particular theorem, it says let the function be continuous on an interval I from the interval a to b with only one critical number, or call it C, in the interval AB. So remember, A and B are both x values, so just a domain. It says if, there's another major point, if the first derivative of C and the first derivative of c is 0, and the second derivative of c is greater than 0, then, kind of redundant, but they're saying f of c is the absolute minimum. And so they have a little drawing here where here's the number line. They have this little interval in green, so I'll just put this in green for you so you understand. This is their interval, I. And then they're giving us some sort of directional where this looks like this, and the minimum is down here, somewhere here. That's basically what they're saying. Same thing as an argument if, and again, this is a point, if the first derivative of c is equal to 0, and the second derivative of c is less than 0, then f of c is the absolute max of f on I. Okay, in this case their diagram looks like this, where you have a number line, interval, call it I, and then their diagram is looking like this, is coming down, and we know that we have a max sitting up here somewhere. And that's the main gist of this. So here we go. Let's take a look at what this looks like on a question, and then we're done, I promise. Very tedious chapter. So this would be your last example in this chapter section, example 3. They say finding an absolute extrema on the open interval. They're asking us to find using the interval 0, infinity. They give us, we'll start with A, and if I have time, I'll do B. All right, so we have f of x is equal to x plus 4 over x. And so if I find the first derivative of this equation, the first derivative is going to give us, remember you bring the x up, unless you want to do the change of base for, or the denominator, because remember this is over 1. So if you do that, you end up with x squared plus 4 over x, and then you do the whole change if you want to, which in this case our first derivative becomes 1 minus 4 over x squared. Okay, which if we factor this, again, same thing, we need to obtain a common denominator once again. So this will become x squared minus 4 over 4, which can be factored further. This will be factored as x minus 2 times x plus 2 over x squared. This should be x squared, not 4. All right, the second derivative, which we also need to find, so this is going to give you 8 over x cubed. And if we look at the critical numbers, going back to this one, your critical numbers, this case is Rx is equal to plus or minus 2. So the only critical number on the interval between 0 and infinity is x minus 2, right? Because I'm only looking at the positive side of the figure. In this case, x equal to 2 is the only critical number. If I pop that into that second derivative, I'm sorry. So the second derivative using 2, we find that this equals 1, which is a value greater than 0. As a matter of fact, we know that f of 2 as a function is 4, right? And so the absolute minimum of f on that interval, there is no maximum. 4 is the minimum. So 4 is the minimum, and there is, based on the theorem I just described, there is no max. There is no max. And that's just looking from 0 to positive infinity. So by argument, we would say that the limit as x approaches infinity of the function that we just described is actually infinity itself. And if you graph it, you can see it. Would you like to graph it for a minute?
Yeah.
So the original is x plus 4 over x. So what did I say here? So x plus 4 over x. X plus 4 divided x. Look at it. We're only looking at 0 to infinity, so I'm only on this side. Right, and we did say x is 2 was the critical number, so at x equals 2, there you are. That's a 2, 4. How do you feel?
Good.
That's what we say, that's the minimum. Okay, so some things to just